temperatures, temperature gradients, dew point gradients, to try and understand how we locate these weather fronts. Ooh, I left my water in the hallway. All right, so you guys, do you still have with you your circulation patterns that you developed? Any chance you have those with you? Yes, that one.
Take care.
Nice colors. That is woo. All right, do you have those handy? Yes? Okay, no? All right, so I'll give you a cheat sheet then if we don't have those handy. Let's see. Go back here. All right, so let's, all right, so if we look at the surface, patterns that we developed when we left off last time. Around a low pressure system, remember, we've got a pressure gradient force that's pushing us from high to low. But what happens to that wind part or that air parcel as it moves across these isobars? Which way is it deflected in the north hemisphere? It veers to the right. We go over to our high pressure system. We've got an air parcel coming out of our high, moving down to our low, and it's also deflected to the right. And so what we set up is a clockwise flow pattern around our high pressure systems and a counterclockwise flow system around our low pressure systems. What this means in terms of, well, you tell me what it means, in fact. So we're taking warm air, which can contain more or less water vapor than cold air. Right, remember the relationship between humidity and temperature? Looked something like this, right? And so as our air gets warmer, it has a potential to contain more water vapor. So a lot of times what we see is these low pressure systems, in order for them to stay maintained, think about this. We've got this wind coming in here. So you might think, okay, as that wind is coming in there, it's sort of putting pressure on that low, when it is. So the only way for these systems to maintain themselves is there has to be a vertical component here. And our vertical component is going to be lift. So in our low pressure systems, the winds are swirling in, but the air in the middle of that low pressure system is actually lifting. When that warm, moist air lifts, it condenses, and we tend to see cloud cover. When we get cool air coming from above in a high pressure system, this cool air is descending. Cool air contains usually less moisture, right? So our cool air is going to be descending. It's bringing with it a little bit nicer, what we consider to be nicer weather, or nicer conditions, not really weather yet. Generally, we tend to think of high pressure systems as being nicer weather because we're getting cool air from above descending. That's what's creating that high pressure. Low pressure systems, we tend to associate them with kind of lousy weather. We get this warm, moist air lifting, condensing, creating cloud cover. Did we look at this already? Okay. We look at these? Okay. I'm not sure how far exactly we
didn't look at the last one you showed.
It's okay. It's not that dissimilar from the we're gonna look at, this is now a map of our current cloud cover. This is a map of our current, no, I'm sorry, this is our predictive. Yeah, this is our predictive. We can see this goes into Friday. It's going very fast. Our ultimate goal here, okay, that's a little too fast. Our ultimate goal here is to kind of understand what these weather fronts are doing, why they're moving the way they are, and what the weather systems are going to look like before, during, and after the fronts pass. All right, that's where we're heading today. All right, by definition, a front is a place where we've got two air masses with densities different enough that they maintain their own, they maintain their identities as air masses. Sort of like in our lava lamp where we've got enough difference in density between these two fluids that it doesn't homogenize, it doesn't mix. Like in our, you put cream in your coffee and it homogenizes and it gets all mixed up. This is keeping the densities different enough that we see separate little blobs. Air masses do the same thing. Warm air masses are going to be less dense, right? Cold air masses are going to be more dense. The fronts are where the two come together. How we define a warm front and a cold front is really great in our color graphics because we have red and blue. But of course, when you go to take a standardized tests, your kids don't have red and blue to tell them warm and cold. So the way we identify these air masses is by the shape of these bubbles. So the round bubbles are like heat blisters. They represent a warm front. The arrows, I don't know, how do you equate that to something cold? Like an icicle, there we go. They're like an ice cream cone or an icicle, so that represents a cold front, right?
Cold air.
Yeah, cold air is going to be more dense, right? Yep. I'm not sure that's how the meteorologists ever designed them to be, so, but that works for us. Go. This is just some of the symbols that we've traditionally used on our weather maps. So you see those little flag-looking things on there? Those little flag-looking things are actually showing us the direction of the wind. And the number of little tick marks on the flag tells us the speed of the wind. So we can kind of see right here, this is a 23 to 27 knot wind right here with this little tag. So our fastest winds look like they're right in here, closest to the center of that low pressure system. Does that agree with what we would maybe suppose based on just the isobars? The isobars are kind of more tightly packed in here, so we might expect a steeper gradient in our pressures. You guys look sleepy this morning.
Are knots, are wind measuring knots the same as measuring knots as like a boat speed?
I believe so, yeah. I believe, yeah. Okay, thank you. The circle, I'm sorry, yeah, let me explain this a little better. So the circle is the direction the wind is flowing toward. The flag is where it's coming from. And, I'm sorry, I kind of assume sometimes that we know that this is described as what kind of wind, a northwesterly or a southwesterly or a northeasterly, right. So we define the wind by the direction it is coming from. So this would be a southwesterly wind here, right? What about this one? What kind of wind is this? Northwesterly wind, right? Does this make sense based on what you know about your circulation patterns? Why? Right, so your winds are going like this, like this, like this. Our circulation system is doing this, so it all agrees. That's nice when that happens. So let's predict. Let's be the weatherman. At position 1, what direction are your winds going to be coming from?
Northwest.
This is a low. Okay, that's an L. I know that's a little bit. Yeah, I didn't draw these. I stole them from someone. All right, so our pressure gradient force wants us to go like this, right? And Coriolis does what? Deflects us to the right. Remember, we have to be the vector. We have to be the wind parcel. We have to follow that trajectory. As we're going across this pressure gradient force, we're deflected to the right. So our wind would most likely be a northwesterly. What about at point 2?
Southeastern.
Yeah, you guys got it, right? So pressure gradient force pushes us this way. Coriolis force deflects us this way. So our wind would be coming from the southeast. What about number 3?
Northwesterly.
All right. So which way is our wind? Which way are we moving? We're going from a high to a low.
Northwesterly.
As we do that, we're going to be deflected to the right. You got to always orient yourself as if you are the wind parcel. So I'm moving this way, deflecting to the right. So I'm a northwesterly wind. See, it's all very simple. You can be the weatherman now, or the weather lady, or the weather person. I don't know what the proper politically correct term is there. So let's kind of put this together in a little bit prettier picture. You can sort of see when a cold front is coming in quite often, well, we are often getting this cold air from the north, right? And so we'll often develop a cold front where the winds are such that they're coming in from the north. We'll develop a warm front where the winds are oriented such that they're coming in from the south. This just makes practical sense. There's nothing. All right, so Philadelphia, remember we talked about this first thing Monday morning, had just experienced these amazingly high intensity, short duration rainfall precipitation events. What happened in Philadelphia? What kind of weather system was moving through there to cause that? This is where it gets really a little tricky. It was a cold front. It was a cold front. And the interesting thing about the weather that develops with a warm front and a cold front has to do with, all right, let me just show you the map first. So this was the map from Sunday. So we saw this cold front was pushing through here. What we often will see right at the front of this cold front line is really dramatic weather, big cumulonimbus clouds forming, lots of thunderstorms, lots of intense rainfall events. So you know those rainy times and it just rains for like 5 days straight and you just, you just get really sick of it? That's not usually a cold front. That's usually a warm front. A cold front brings with it pretty dramatic weather and pretty intense weather. I'll show you this in a second in a graphic. Actually, in literally a second. So we have a cold front that moves in. It is a cold, dense air mass. Here's the front, where these little arrows are. It has, because of its density, it tends to form a pretty steep angle with this warm air that it's pushing up against. When that steep angle is formed, we create these huge towering clouds along this steep angle. These are our thunder clouds. We like to, associate thunderstorms with this huge vertical building of clouds. That's because this cold, dense air is kind of hugging the ground, and it's really forcing that warm air to come up at a pretty steep angle. The weather in front of the front is going to be crappy. Actually, the weather in front of all of our fronts is kind of going to be not very nice. It's what happens after the front passes that it's pretty different. After this front passes, we get cooler air mass subsiding, we get clearing conditions, and our pressure goes what? Which direction? I know it's up there, so I kind of gave you the answer before I meant to. It does. Why does it go to high pressure after the cold front passes? Okay, if I'm standing at the letter C, pressure is low, and then after the front passes over me, the pressure is high. Why?
Cold air is descending, so low pressure is coming down.
Yeah, so you've got this cold, dense air now. This cold, dense air represents higher pressure pushing down upon the atmosphere, or upon the surface of the Earth. So we end up, after a cold front comes through, with Bing. Somebody was picking on me for my choice of 80s music, and I said, just wait till tomorrow, it gets much, much worse. All right, so after our cold front, we end up with nice, clearing weather. All right, our warm front is a little bit different. The warm front is the advancing front. It is the one pushing into the cold front. Because it is the advancer, it has a slightly different relationship as it's moving in, and it creates a little bit of a shallower slope. So what happens is that our cloud cover, instead of being tight and high, tends to spread out. So if you start seeing these large, wisps of cirrus clouds up in the atmosphere, chances are what you're going to see next are the formation of stratus clouds, which are kind of layered clouds coming in behind it. So when you see those cirrus clouds and you think, oh, that's kind of a pretty day, what's going to come behind it in a few days may not be as nice as what you had thought might be coming. We tend to see moderate precipitation over longer time periods. That all comes from the relationship of these fronts and their slopes. So the steep slope kind of forces things to happen quickly and intensely, and the shallow slope spreads spreads the lifting of this warm, humid air mass over a larger area. After this front passes, if we're standing at the letter M, this front, we're getting rain. After it passes, what's going to happen to our pressure? The pressure is going to go down, right? Our cool air is denser, it puts more pressure on us. Our warm air is less dense, and it gives us a lower pressure system. Let's see if this works today. Oh. So, as this front is moving through, this is the song that we might think of to associate with that passage of the warm front. And I think this is the last piece of cheesy music that I have for the day. All right.
This animation is going to describe
Let me turn him up.
Precipitation happens at what are called cold fronts and warm fronts. These are weather systems that develop wherever masses of cold air collide with masses of warm air. And the name actually comes from war, where armies would meet along a battle line called a front. And one way to think about the difference between cold fronts and warm fronts is to think about which mass of air is going to win the battle. So we'll start with a cold front. This is a situation that happens where cold air moves in like a big wedge underneath warm air. Cold air is always heavier than warm air, and so it's denser, and it's going to tend to slide under the warm air and push the warm air upward. Anytime you have air rising upward, it's going to expand and cool and lose its ability to hold moisture, and this will give you a band of clouds and precipitation along the cold front. On weather maps, if you watch the weather on the news, you can see cold fronts marked by lines of blue teeth that point in the direction the cold air is moving. Along cold fronts, you typically have very intense local thunderstorms and rainstorms, so it might pour rain for a short time, but then quickly, usually within an hour or so, the front will have moved on. So a cold front is where the cold air pushes underneath the warm air, and you have high rainfall and usually intense thunderstorms. Now, the warm front has in common a couple of things with the cold front. One is that the warm air still goes up on top of the cold air, but in this case, the warm air is actually pushing the cold air out of the picture. So the warm air is winning, and that's how you can remember if it's a warm front. The warm air pushes against the cold air, squeezing it out. Like imagine squeezing a watermelon seed between your fingers. It kind of squeezes out, right? And as the air pushes, it also rises up over the cold air. Rising air, again, loses its ability to hold moisture, and you tend to get clouds and rain. Along warm fronts, you typically have more mild, more mellow, more spread out rainstorms rather than really local intense thunderstorms. And if you're looking at the weather on the news, they mark warm fronts on maps with red half moons that point in the direction that the warm air is pushing the cold air. So that's cold fronts and warm fronts, major precipitation belts in many places on the Earth.
So does it make a little bit more sense now if we think about Philadelphia's weather on Sunday? The fact that we had this really short duration, intense rainfall event dropping 8 inches of rain was not related to a warm front which spreads its rainfall out over a large regional area, but to this cold front that has a really steep slope, and this energy is very concentrated over a small regional area. So that's when we get these pretty dramatic weather patterns. All right, so anybody remember a little game show called Name That Tune? Us older folks remember that. The rest of you probably have maybe heard reference to it. I can name that tune in 2 notes, George. All right, so we're going to name this front in 1 clue. You guys are my high school teachers. 1 clue. What front is this? All right, guys, time for you to all get your arms out. Get your wind vectors going. Before, winds are coming from the southwest. Southwest. After, winds are coming from the
Cold.
okay. We said cold. Should we see if we need any more clues that'll support that? Let's see. This was not cooperating yesterday.
What are the bars? What are those color gradients on the side?
These bars?
Beside dew point? White
Oh,
dew-
that's me hiding the data from you. It's
Oh.
supposed to magically
I thought it
disappear.
was something-
No, I'm sorry. My animation on this doesn't work quite well, so I can't figure out why. I tried to fix it last night, and it worked fine, and then it doesn't work. So I'm kind of at a loss here. Oh, there we go. See, it just keeps popping up all at once. So for whatever reason, I need to fix that animation. This is still the one we were working on. All right, so the next piece of information, try to ignore the other stuff here. Let me get rid of this. Oh, see, now I can make it go backwards, but I can't. That's what I have to do. Forward, backward. So our dew point, remember this line that I just erased? Defines our dew point, humidity versus temperature. So what we see is that our dew point is high, and it's starting to lower. So what does that mean, probably? Does that agree or disagree with your assessment that this is probably a cold front? It agrees. Yes, I agree that it agrees. Oh, it just worked. The pressure is a good clue. As the front is coming, it's falling, it rises very quickly, and then it rises steadily. When we see rising pressure, we associate this with cold front. So yes, 3 clues all agree with your earliest assessment, which was awesome that you got that from 1 clue. I just have to tell you that. Precipitation, little bit of showers, heavy showers, rain or snow, thunder, hail, and lightning, and then we're eventually going to see clearing. This also agrees with our idea that this was a cold front. The last clue is kind of the giveaway because we end up with cooler temperatures. So, not surprisingly, let's look at this one. Let's make sure we're not just guessing based on powers of deductive reasoning that this is a warm front. So our winds are starting from the south-southeast, and they're going to change to south-southwest winds. Our dew point is steady, and then it's going to rise. That is corresponding with a rise in temperature. I think we're right. Our pressure is going to fall. When does the pressure fall? When the warm front comes in. Our precipitation, it looks like drizzle, 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 crappy, crappy, crappy. That kind of is what we associate with a warm front. And warmer temperatures. It's cool, steady rise, eventually warming. Got it? Makes some semblance of sense? Okay. So let's take a little quiz. So get out your cell phones or your iPads. Let's see how we do. This is one of those awful, awful rule out everything questions that we all love to hate. After a cold front passes, which of these does not usually occur? You are going to send your message to this number, and then you have to put in the context, or in the text itself, one of these values. Just like we did yesterday. Well, Monday, whatever day it was I saw you. This is after the front passes. Okay, so after that cold air mass has moved across, what is the least likely thing that we would see? It's not working? What happened? Oh, you know what? I may not be logged in today because this is the first poll. I'm sorry, guys. I was like, you guys are really thinking about this. Reload. Oh, maybe I'm just logged out. All right, let's go back and check that. Yeah, this logged me out or something. So, connect. All right, so raise of hands. No, let's not do that. Okay, I believe this should work. As long, I'm not, I'm not sure if I'm logged in to Poll Everywhere, if that keeps me logged in or not. But it's thinking, so that's a good thing. Oh, there we go. Excellent. A little bit of internet connection always helps if you have web content. How'd we do? 5 of us believe it's letter E. 2 of us so far believe it's letter A. Really, we see winds shift with all kinds of fronts. It's a warm front, so by definition, we're bringing in warmer temperatures. So we're going to see the temperature rise, not drop. So we can rule out A and B. We, with a cold front, well, we didn't really talk about relative humidity. So that one I can see where we got a little confused with, if you weren't sure about that one. Letter D, clearing skies. You guys all picked up on the blue skies thing. So yes, we've got the cold front, we've got the nice clearing skies. Thankfully, the majority of you all agree that we would not see a decrease in pressure, a falling barometer. Okay. Maybe the way that this was worded was confusing. But the wording of this, I pulled directly off of like a Regents test purposefully, because you guys know sometimes the way things are worded on your test and the way you present them is ever so slightly different, and it's not always easy for a student to say falling pressure or falling pressure is the same thing as a falling barometer, especially when your teacher just gave you this barometer over here that goes the opposite direction. So I had someone point this out to me yesterday. Well, the water level fell. I said, but remember, this is a very simple device. When this water level falls, it's because the pressure of the atmosphere is pushing down on it. So I kind of set up a confusion right there, didn't I? So it was a good teaching moment for me to realize this. So I decided, I said, you know what, I'm going to go home and change it last night. And then I thought about it and I said, no, I think it's a teachable moment, so I'm not going to go home and change it. I'm going to leave it. You see where I'm coming from? Yeah. I've been talking about a decrease in pressure. I have not been talking about a falling barometer. So the terminology sometimes is confusing, and our demonstrations sometimes can lead to confusion.
So a falling barometer would mean an increase in pressure.
Falling barometer means a decrease in pressure. A falling barometric pressure reading.
Okay, but according to that, more pressure that goes down. I know.
Exactly. But if you're looking at a mercury barometer, which is, a more scientific, this was a very simple demonstration. A mercury barometer has basically a chamber of mercury with a tube in it, and it's open to the atmosphere. So as the atmosphere pressure pushes down on it, this mercury level will rise. Okay? So a falling barometer means falling pressure. Okay? So that's what I'm saying. If we have some confusion here, it's understandable. Because if you're looking at that and looking at this question, then in your mind, you may not be thinking lower pressures. You know what I'm saying? Does that make sense? Falling barometer means lowering pressures. All right, so traditionally, this is what weather maps looked like. And I don't know about you, but that kind of makes my head hurt to think that I would have to analyze something like this. Okay.
Last part of it. After cold front passes, wouldn't that be the warm areas moving in?
No, after the cold front passes, let's look. Let's go back here. Okay, sorry. Okay, the cold air is moving in, so we're standing at the letter C, right? So after this front passes by us at the letter C, we've moved this. The air gets colder, the pressure gets higher, or we have a rising barometer. That's another way to say that, which I never would say. Sorry. Does that clear that up?
Yeah.
Okay. All right, so our weather maps now don't quite look like this because we have really nice computer processing systems that enable us to show things in color. So we're going to step through various different types of data, and I need a volunteer from the audience who's always wanted to be a weather person. Come on, somebody has, okay, even if you never wanted to be a weather person, somebody that's willing to stand up in front of the class with the video rolling and be come on, I'll pick on you.
I'll do it.
Oh, thank you. We have a weatherman today. So what he is going to demonstrate for us is where we see the first piece of data we're looking at, which is a gradient in temperature, which is shown in yellow. We're looking for a very, very steep gradient in those yellow lines.
Right in here somewhere.
Okay, you got to do the swoop. You got to be.
Right in here,
Be-
we're going to have a gradient in temperature.
Let me show you how it's done.
But your back's to the camera. so
You're
you
right,
have
you're right. You're right, you're right, you're absolutely right. How they do this, it's kind of funny to watch them, right? Because they're looking at a screen over here and they're looking at the camera and there's nothing behind them and they have to make their hand go in the right
Okay,
direction.
so really I should have a blindfold on.
There you go.
Here.
We got it. All right. So he's identified a steep gradient somewhere in here, right?
Right.
And that's temperature. Let's look at our next data. These are dew point values. And yeah, okay, so there's some negative values this way, positive values this way. Don't worry about the numerical values so much. Look for the steep gradients again in the blue lines.
Same place.
Yeah, so you see similar kind of swooping behavior of these dew point gradients. They kind of align so far, right? All right, this one's easy, right? So this is the pressure gradient map. The blue lines are pressure gradient. The solid blue lines are decreases, and the dashed blue lines are decreases. Increases, the opposite of, yeah.
Right.
So just to be clear, these yellow lines represent the wind vectors, okay? We can just kind of look at the pressure gradients here. Let's just do that one rather than the wind vectors right
So what am
now.
I pointing out?
So show me the blue line steep gradients again.
And I'd say this is the most increase.
Okay, you're identifying some pretty strong wind vectors here and change in direction here too, right?
Yeah.
Yep. Okay, we might also consider cloud patterns. Slightly different map outlay here, so it's a bit of confusing, but you can see sort of a band of rain or some sort of thing the radar is picking up. The clouds are a little messy in this case. They don't really point things out for us that clearly. So, in the end, have we identified probably a cold front, a warm front,
I'd say cold front.
cold front?
Yeah.
Okay, so you're using the wind vectors as evidence that we're bringing down cold air, right? Okay, let's see what we actually found. So go ahead, tell us. What did we?
We have a cold front moving in from the northwest, while a warm front is moving up from the Gulf and coming over the top of the states.
You could be Jim
I'm
Cantori.
telling you, we have a high pressure gradient coming through right here, as well as up here. I mean, I don't know what these purple guys are, maybe a bathing suit weather up in that area.
When you have two together, that's stationary. That means nothing is really overtaking the other. So now, Jim Cantori, tell us, what's the weather going to be like after this front passes through, oh gosh, I can't even
We
see
got
which state.
Tennessee right
Yeah,
here.
we've got Tennessee right here. So in a few days, what's the weather going to be like in Tennessee after this front
After
passes?
the front passes, you're going to experience some cool weather through the day. Maybe a few days after, then you get back to some warm, low pressure areas back here in the.
What's going to happen to you in Tennessee before, if you have a golf day planned
You might
and
want to reschedule.
this is coming in, what's going to maybe happen to your golf plans?
You're going to get rained out. Tea time, 4 o'clock, cancel.
And why?
It's going to pour down rain.
Really long, drawn out
No,
rainy
just
days?
One or two,
Okay.
maybe a day and a half.
Okay.
at most.
Thank you. Very nice. If teaching doesn't work out for you, there's always on-camera weatherman or whatever they call it. Summer.
Tornado.
Kind of give you a little clue that we're going to have a lot of rain. Probably a lot of high-intensity rain. In the summer, we usually see these coming through as thunderstorms. Yeah, severe thunderstorms in this case is what they were predicting, coming down off this cold front.
Now, when you have like extreme drops, I lived out in the Midwest, like right where the big yellow, and it would be in the summertime, maybe 7 o'clock at night, 114, 116 degrees, and within a half an hour, it might be 58.
That's a really great question.
And we
You're-
would get hail like huge. I've been out.
Why do we on the East Coast tend to see less temperature variation between our daytime and nighttime temperatures? Generally. We have a lot of moisture. The moisture is a great holder of heat, right? Out where you're talking about, there's so little moisture.
50% humidity makes
So when the sun goes down, there's no latent heat stored in your atmosphere. And so your temperatures have this beautiful drop at night. We see those here when we see our humidity plunge. And that's when we get, nights like we had at the beginning of the week, which were just gorgeous. Our humidity level was down like at 45 or 50, which was nice, for us in the summer.
Actually, that's tornado weather.
Yeah.
That's extreme.
You lived out where?
It's like 200 miles east of the Rocky Mountains.
Okay, nice.
But it's real flat there.
Yeah.
It would just blow when a storm would blow in like that. You could just
So you, yeah,
I mean, it was just extreme drop in temperature.
right, right. And
The rain was ice cold, ice cold. And here it's very warm.
the rain was ice cold. Okay,
Even
Interesting,
when it
yeah.
rains here, it rains.
warm.
It's warm.
Yeah.
Yeah, it is warmer than.
Yeah, that's a great interesting point, that the humidity level in the air will absolutely affect what happens to the changes in temperatures throughout a day, and throughout a season for that matter. I think we may be finally coming to the end. We're not going to belabor this point. You guys got this. Oh, I know what I want to show you. This is kind of a cool site where you can go and you can make your own maps, and you can pick your data to be plotted data, so it's like little points on the map. You can pick your data to be contoured maps. You can pick it to be many, many different displays, but it's kind of cool because it gives you real-time data. So, you know, if you're perchance teaching a weather unit with your kids and you want to say, well, let's go see what's actually happening with temperature. Or I'm going to pick a contoured surface data map. What variable should I choose? Let's see. Let's choose the Mid-Atlantic. Let's choose maybe sea level pressure. Let's see what it gives us. Oh, that's pretty spacey. Let's try it again. The interval was, we don't have a big gradient in pressure going on right now, I guess. Contoured. Let's look at temperature. So what we produced was a real-time data contoured map of our temperature gradients right here, right now. Instant gratification, instant data. You could relate this directly to weather patterns that you're seeing outside with your students. It would be kind of fun. It's kind of fun to have real-time stuff sometimes. His phone just started talking to him. Oops. So when we put these all together, what I have showed you, we haven't really even talked about radar, but this is a map that you can pull off of, you can pull from NOAA data, which actually overlays everything. It's kind of nice. So we can see these precipitation patterns as this cold front is pushing out to sea here. We can see the isobaric pressure lines, the isobar lines. We can see we have kind of a crazy system developing here, sort of a stationary front. Things seem a little kind of sleepy right now. Not a whole lot of strong pressure gradients being set up. Nothing like what blew through earlier in the week. All right. And with that, we're going to take a dramatic jump. There's no easy segue here. We're just going to move out of our meteorological systems and on to the next topic that we need to cover, which has to do with movement of heat in the earth. And ultimately, if we're very lucky, what time are we here till 11? Okay, yeah, we're only going to get through movement of heat in the earth today. I can kind of guarantee that. All right, so you guys were asking, I forgot the first day to put my email address up here for you, but here it is. So it's just skauffman@alb.edu. And I told you that I was trained as a geologist. This is one of my all-time favorite Calvin and Hobbes cartoons. Calvin reminds me so much of my son sometimes, it's frightening. Geology is not a real job, so I don't ever have to worry about losing my real job, my non-real job. So how many of you guys actually teach solid earth science? You know, talk about the cores and the layers of the earth, and okay, so a handful. We show our students these pictures, and we show them pictures that the earth is broken up into layers. It has a crust, it has a mantle, it has an outer core, it has an inner core. What do we know about the outer core that's different from the other layers? Is it a solid or a liquid? It's a liquid, right? Oh, actually, this one gives it away, sorry. it is a liquid out here. The inner part of the Earth is a solid. Why? Yes, thank you. It's pressure, right? There's a delicate relationship that develops between temperature and pressure such that, you know, you guys have an appreciation for it, your science teachers. Most of my students that come into me are non-science majors, and so they don't really have an appreciation for the fact that you can change not only temperature but pressure to affect the phase. So we could take solid Earth, this is a phase diagram for water, but we could take solid Earth in the same way, and we could decrease just the pressure, do nothing to the temperature, and we would move from a solid phase to a liquid phase, right? Where do we see this example actually taking place in real life? Where maybe the temperatures, right, an ice skater maybe? An ice skater going across the ice is actually putting enough pressure on that ice to turn it to a thin surface of liquid water. The temperature is really not changing that much. What's changing is the pressure. The other thing that I find interesting is that sometimes people think that we've actually drilled down into the Earth pretty far, and I can't blame movies on this, but yes, I can, because all of these crazy movies tell us that we've gone down to the center of the Earth, and Jules Verne had this fantastical notion that we got there. I love Brendan Fraser. I love that movie. It's so kitschy, but I love it. Journey to the Center of the Earth, have you seen it? Some of you maybe. It's fun. They mention minerals in that movie, so, you know, there's not many movies that mention feldspar and muscovite and garnet. And actually, the deepest we've gone right now, although somebody tells me, is James Cameron trying to drill? Somebody's got a mission to try and drill really, really deep into the mantle? No, you guys aren't? Okay. I have to look this up because it sounded a little different than what I knew. But right now, the deepest borehole the humans have drilled into the Earth is about 12 kilometers deep. Our mantle, we don't reach until we get to about 40 kilometers on average. Our crust is different thicknesses in different places. So we haven't even gotten past the outer eggshell layer of our Earth. So how do we know that these layers are what they are? How do we know there's a liquid outer core if we haven't gotten there to sample it? Speculation. Volcanoes aren't actually fed from this liquid. Volcanoes are fed from melting mantle, okay? So, but you're right. A student would look at this and go, oh, this is the source of volcanoes. It's the source of heat that eventually feeds the melting of the crust, but it's not the source of the liquid magma that comes up to the volcanoes. If it were, we would have a perfect opportunity to sample the core, the outer core. We can't sample the outer core. Anybody else have any ideas how we know this? Seismographs, yes, exactly. So something fun happened once we started instrumenting the Earth with seismographs. After the 1906 earthquake in San Francisco, big one, we started implementing a global pattern of collecting seismic data. And what the geophysicists very quickly realized was when an earthquake happens here, we see these primary waves, the P waves, coming around and transferring their energy all throughout the entire Earth. But we don't see S waves doing the same thing. S waves will travel no further than 105 degrees away from the center of this earthquake. Why is that, do you suppose? Yeah, they can't travel through liquids. S waves are waves that travel by the change in shape. And so the parcel that it's traveling through has to have the ability to bounce back into its shape. If you throw a liquid out of shape, will it bounce back into its original shape? If I have a beaker of, I don't suggest doing this, if I have a beaker of water on my table and I break the glass, will that water bounce back into that beaker shape? No, it won't. So S waves, by the way that they're propagated, cannot go through liquids. P waves can. And the other interesting thing is if you note, the physics here a little bit, you can see that the P waves don't go through in a straight or, a consistent fashion. Once they get to this liquid layer, they're deflected and refracted. And so we can look at the physics of that and also have like sort of double support from the seismic data. And that's how the geophysicists discovered where this liquid outer core probably is.
Do they do this with every earthquake that happens?
They collect data all around the Earth. There are probably, for every simplification, like a picture like this that we show, there are going to be geophysicists arguing about exactly where this boundary is. We have a general sense of where it is, but different models will show different exact locations. So yes, if you go to a geophysics conference, you're going to have people probably still arguing about everything that I present to you. We like to present science as if it's, and maybe in physics they can do that, but in geoscience we still have a lot of unknowns. So the heat is coming from within the Earth, we know this, and it is, slowly we are cooling down the Earth over geologic time, right? The Earth is still very hot in the center. What do you think? I tell you here that the two sources of heat are radioactive decay and this residual heat due to the gravity, the gravitational pull from the original formation. Which of those do you think is probably the greater source of heat? The formational heat or the radioactive decay heat? Yeah, they estimate right now, again, this is a topic that is being debated, but about 90% of the heat that is generated inside the Earth, which is, being conducted and convected out of the Earth, about 90% of it comes from radioactive decay. We know that when we take a radioactive element, okay, I just have to tell a story. So we went out to dinner last night at the poorhouse, and there's this guy sitting at the bar, and he's got like a softball shirt on or something, and the name of his team on the back is Isotopes. And it took everything within me not to go ask him where the heck he lives or what team he plays for that has the mascot Isotopes. So does anybody know? I was thinking maybe Limerick, but.
I know those guys.
Oh, okay, so where are they from?
They work.
Are they science people?
They work at Vanguard.
Okay,
which is in
okay.
Vanguard.
So I said, we were discussing it. I said it either has to be some kind of scientific firm that has geeks that would just think this is great, that were called the Isotopes, or maybe Limerick, where they would have another appreciation for that. Okay, thank you for clearing that up. I'll be happy I can share that information with Dr. Berkey. So we know that when a radioactive isotope decays, it releases heat. This is how we're generating nuclear thermal electricity. So if you look actually at the heat that's being released, this is billions of years. So the Earth started here. The Earth is here, right about here now. And we can look at radioactive decay of uranium-238, uranium-235, thorium-232, and potassium-40. We add them all up, and this is what the heat release over time has looked like. So absolutely within these first, 2 billion years of Earth's history, things were a lot hotter. This heat is on a decay curve. It's on a pretty dramatic decay curve such that we will eventually get to a point where it goes down to 0. Will we have to worry about that? Not so much. By that point, something really dramatic is happening, right? We're getting sucked into a star or something like that, they tell me. We also know that chemically, the Earth is different physically. It's also different chemically. If we look at the whole Earth, the majority of the elements in the Earth are iron. However, if we look at our crust, only a small percentage of the crust is iron. Our crust is made up of primarily oxygen, silicon, and a little bit lesser aluminum. These are our geologic building blocks. The beautiful thing about geology is that when we have to deal with chemistry, we deal with about 8 things. So it makes it really user-friendly for a non-chemist to come into a geology class. And I have my students make themselves into silicate models and all kinds of crazy things. I do such crazy things, they think I'm nuts. Okay, so we are continuing to create, or there's heat that is continually escaping from the Earth out into the atmosphere. This, in part, is taking place in the mantle, where we've got this idea that there are some sort of convection currents driving movement in the mantle. And I know what I forgot to give you guys. There we go. So we're going to grab some silly putty. Go ahead and take it out of its little egg.
I made some silly putty this morning.
You made some? Mm-hmm. How'd you make silly putty?
Borax.
Oh, with the, okay, yeah. The borax silly putty. Does it work exactly the same way? Oh, that's cool. It's what? Not exactly. All right, you may have to share an egg or two here because I think I just ran out. So if you guys could share behind you. Here, you guys take that one. Thanks. I can. I'll have these up for you too. You can. It's easy. Can I have them here? Got it. Got it. All right, so silly putty is a solid, a liquid. Oh, I forgot about this.
Need some borax, silly putty?
Huh?
You need some borax, silly putty?
Do I need some? Do you have some? No. No, someone, okay. So let's get to the question first. When you picked up your silly putty and looked at it, was it a glob? Was it like shaped like the container? So, okay, so we were playing with these yesterday. So between yesterday and today, they went from whatever ball they put in there to something that shaped its container. So it's behaving liquid-like, right? So what I was saying ought to is somebody made me a die yesterday. You know, he put all the little dots on all the different sides of the silly putty, and now it's kind of, you know, conforming to the bottom of this egg, and it's no longer a die. So, yeah, there we go. It's kind of flowing. This is not a perfect analogy, but it's a decent one when we think about what the mantle is doing. The mantle is not bubbling goo of magma. It is a liquid in this, it is a substance that can flow over very long time periods. So, let's take the temperature of the room here a second. Those of you that do any kind of plate tectonics with your students, how do you describe to them what drives the plate movements? Convection? Okay. So you actually do introduce slab pull. Okay. That's not always something that that people introduce. Anybody else? Our traditional diagrams and pictures and our traditional scientific ideas behind how plates were moving were this idea that we have a convection current which is pushing magma to the surface, allowing these ridges to split apart. The ridges are splitting apart, these mid-ocean ridges like the Mid-Atlantic Ocean Ridge. Absolutely that is happening. Originally they thought that this was the driving mechanism. Now the more widely accepted driving mechanism is the gravitational pull of this slab as it's being subducted. Subduction is the process by which one plate slides underneath another plate. The convection currents are cycling heat through the mantle. The plates, the lithospheric plates, the crispy stuff, the brittle stuff on top, it's not a passive passenger. It's not just being carried along. It's actually contributing to the movement. So the density of these plates, combined with the force of gravity, is pulling this plate down. This is referred to as slab pull old, dense, heavy plate sinks. Ridge push was kind of our older idea. And sometimes, some textbooks, depending how old your textbooks are, will bring this into the conversation. More often than not, the textbooks misrepresent this as being the most dominant force. So your text actually brings in slab pool, or is that just you?
Yeah, it has all three of them.
It does.
It has a diagram somewhere, yeah. It
No.
doesn't mention it in detail.
Okay, but it says that they are occurring. And so it doesn't tell you which is dominating?
I don't.
Okay, all right. Well, okay, that's maybe then an important point because we really did think that the ridge push was the dominating factor. But the geophysicists say, wait a minute, let's look at how fast these plates are moving around Earth, and let's actually assess the plate movement and compare it directly to the mechanism that's moving that plate. So they looked at the Pacific plate. Pacific plate has a large margin of it that's subducting. It has some of the highest velocity vectors. All right, so these are vectors. The length is indicative of the magnitude, and of course the direction is the direction. So this is our Pacific plate. For those of you that aren't earth scientists or teach it, the Pacific plate is also known as our ring of fire. It's where 90% of our earthquakes, volcanoes occur, right around this plate. It's a very active margin. This whole area of the Pacific plate is a subduction zone. So they took together information about the Pacific, the Cocos, the North American plates, all different plates. And they found that the plates that have most or a large margin of their represented by subduction zones are correlated directly with greater movement velocities. The slower moving plates, where's North America, like here, have much, much smaller proportion of their total margin represented by these subduction zones. And so this is where we get the idea that perhaps it's this slab pool that is driving the plate movement. All right. So let's just look at this in a little bit more detail. The original idea of ridge push was that we would develop a slope here from this magma, which is ascending. This slope then set up a gradient for gravity to pull, or for gravity to allow this plate to slide. Okay. So there's this interesting little flip in density right near the very uppermost part of the mantle. Do you see that? So we've got a high density here and a slightly lower density right here. What's going to happen if you have something that's lower density below something that's higher density and it has the ability to move? It's going to try and turn itself over, yeah. So they're also looking at this, the higher technical type measurements we're able to get on density. They're looking at this as a potential mechanism by which we're starting this churning process that wants to pull this more dense plate down along the subduction surface here. It's sinking, it's being pulled down due to gravity and due to its greater density. I think it's nicely summed up. This was a gentleman who studied this pretty intensely from Japan. Basically, that subduction plays a more fundamental role than seafloor spreading in shaping the Earth's features and running the plate tectonic machinery. Now, we talked about convection cells. When you think about a convection cell in the mantle, do you think about it as looking, all right, so my crust is not drawn to scale, so this will be our mantle here. Do you think about it looking like this? or looking more like this. I don't even know if I can draw the second one. All right, a mess, basically. Which way do you picture it?
It's the mess.
This is the way our textbooks picture it, right? This is the way we show it, and this picture is still in text. You know, this is a text that I teach from. Still, this is how we show it. This is very hotly debated, and the geochemists and the geophysicists do not agree on this at all. The geochemists say that the geochemical data just does not support the geophysicists' idea of mantle convection, and so there are these two contrasting ideas. Is this a convection cell model or a mantle plume model? And the mantle plume model sort of is suggesting that we get these sort of hot spots of magma which come up in very irregular patterns. It's not as simple as a homogeneous system with one big cell moving around. That makes intuitively more sense to me because we know nothing in the Earth is completely homogeneous. There's going to be all kinds of irregularities that would cause weak spots or hot spots to develop.
Would that account for that hot, what it looked like it was a hot spot in the Pacific?
In Hawaii?
Such dramatic.
That's exactly some of the reasoning that they're using. So they're saying, okay, folks, you present plate tectonics as all the margins are the volcanoes, and then boom, you put Hawaii in the middle of a plate. So this is where the geochemists come in and say, let's rethink this model of convection. And they're coming up with this idea that, I think this slide shows it. This is kind of messy. And I have to tell you, is this not the ugliest image you've ever seen? Whoever chose this color scheme, I said, maybe we're just colorblind. I think it looks like a lung or something. Maybe it comes from a medical, it's bizarre. But anyway, this is sort of kind of the current thinking of how, instead of being beautiful convection cells that are stirring things up, they believe that there's more like these sort of like spurts of stuff. And when I say spurts, I'm not implying quick movement, okay? This is movement over slow geologic periods. Geologic time, which we know is the length of my arm span. You'll get that joke in a second. So yeah, so we may have little hot spots coming out in the middle of a plate then. So we're still evolving in our understanding of how the Earth is working. There's a really cool app that is not free that's called Earth Observer. It's 99 cents. That's not this one, but we were looking at it yesterday. I wasn't going to point it out because it does cost money, but it's all of 99 cents. And it is so cool because it shows you the rates of plate movements. It shows you all kinds of really neat data. Earth Viewer is the one that I had on this presentation because it is free, and it also has some other cool features. It allows you to, let me see. The other one was called Earth Observer. I don't know if I can load this.
For 99 cents, I'll believe you.
99 cents, you know, that's how I am. I'm like, if for 99 cents I can play with it, you know, it's cheaper than a coffee. So this is the one that I have up here. I don't have a document camera that I can share this in any nice way with you, but basically the cool thing about this is you can, if you're talking to your students about geologic time, you could actually say, okay, we're looking at a fossil from the Jurassic. Let's go up here and let's go see what the plates looked like. All right, so our fossil, oops. How do I spin this? I guess that's it. So our fossil was found in Ohio. Let's look and see what the climate might have been like in Ohio based on where the plates were oriented. We could also go down here and say, let's add, where is it? You can add other, you can add biological events, geological events, mass extinctions, impact events. So as you're moving through here, through geologic time, you could say, oh, boom, this is when the first land plants appear. Look how the plates are oriented. You know, it sort of puts a nice visual with all of these linear timelines that we always talk about. Let's see what else happens. Here's a huge extinction event in the Permian. course, we all know about the one that kills off the dinosaurs. But anyway, this one was free. It's kind of fun. I like the idea of being able to look at where the plates were during different periods of time. You're here till 11, right? Okay, or so. All right, this is where my joke was going. So this is one of my favorite demonstrations of the geologic time scale. So everybody stand up, please. Actually, I need 3 of you in the front of the room. 1, 2, 3. You guys come up here. You'll be my universe time scale. It's short. Not a long time. You have to stand up here. Okay, spread your arms out and stand arm length to arm length. All right, he's green, so he's going to be my Earth. I don't know why. He's my Earth. This, beginning of the Earth starts here, and this is current time here. She represents over there what? At the tip of her finger. Right, this is the Big Bang over here. So you need 2 total Earth time spans before we even get to the formation and the beginning of Earth itself. Okay, you guys can sit down. So now what we're going to do is walk through ourselves with our arms spread, geologic time according to our carry-along time scale. At the very, very beginning of one end of your arm is where we have the origin of the Earth. I guess I should do it this way. As we move along your arm span, right about your, I was having a hard time yesterday with the anatomy. I kept calling elbows, shoulders, and right around at your elbow, we see the first earliest life forms. It's not until about your nose, right at the middle point of Earth's history, that we actually start to form our large continents. Right about your shoulder on the far side is when we start building up oxygen in the environment. Before that, the algae had not been around long enough to produce the level of oxygen that we need for multi-cell life forms. Okay, let's move along here. Trilobites appear here. Fishes, corals, amphibians, reptiles. The dinosaurs represent about this much of your hand. So from this knuckle to this little knuckle, they were pretty successful. Mammals come along way out here. Humans, it is a emery board along your fingernail, and the dust that comes off of it is us. So I use this, I demonstrate this to my students, and then as we're going through the semester and we're talking about periods in geologic time, I'll bring up the fact that, remember, we hadn't even built oxygen into the atmosphere because we're still on this side of our body. It's like the Weather Channel version of the geologic time scale. You can use your arms. All right. I am going to have to pass along the next piece of what we're going to do to your satellite professors. We had a little, I tried to leave the more logical, easy to grasp stuff till the very end, because most of what you need to address is looking at the logical sequence of events throughout geologic time. So you can do that with each other, with your satellite professors. And we will, I think, finish there today. Let me see what else I have to give you. You know what, let me make sure I give this to you. This says summary.